Assalamu alaikum, dear students. Hopefully you are well and fine and must be catching up with the lectures on time. Dear students, the good news is that today we are going to indulge with the last topics of this chapter number 1. Inshallah, today we would be done with this chapter. The aims and objectives of our today's lecture are, we would inshallah talk about a little bit about the thread. We will talk about the differences between process and thread, as we already have discussed this topic of processes in our previous lecture. We will talk about multi-threading, then we will talk about certain phenomena which actually relate back to the functions of an operating system or to the types of an operating system. So we will discuss these phenomena like multitasking, multiprogramming, and multiprocessing. So basically you need to know is that what is a thread. Let's have a glimpse of the previous lecture in which we talked about program and a process. That a program is a set of instructions, and these set of instructions are actually there to get used by the user in order to perform some certain tasks. So a program or a software is actually a set of instructions. So processes belong to these programs. When we apply some instruction inside a program or a software, we say that we have started a process. Every single instruction actually initiates a different process. And when we start some process, inside a process, certain threads exist. Actually, when we apply some option or instruction inside a software, we initiate a process. Behind that process, behind the scenes, some other invisible instructions are carrying on. I'll give you an example in order to clearly grasp this concept. Let's suppose you are using MS Word software. Now, MS Word is a program, is a software. Then inside that MS Word or software or a program, you are using certain options or instructions. Let's suppose you can say you are using an option of equations, you are using an option of font size, you are using an option of background color, page indents, or font styles. These all options or instructions are present in the interface of MS Word. So MS Word is a software program in which these certain options or instructions are present. When you click an instruction, for example, on your data, you want to apply some other or different font style. So you apply this instruction on your data. You are applying actually an instruction or option, and you are initiating a process by applying that instruction on your data. So your instruction is font size, you clicked it, and you started a new process inside that MS Word program. Now, what is a thread here? You know that you have applied that instruction font size on your data, but you can feel that behind the scenes some other instructions, some other invisible instructions are working. So the instruction is of font size in MS Word, which you would apply on your data, but behind the scenes an invisible thread is continuously being applied and executed, and that is of depicting or displaying the blank page for you, displaying that data on that white page for you. That is also an invisible thread, that is also an invisible instruction, that there is some thread which is continuously displaying that white page, white electronic page, white interface for you. There is some invisible thread that is actually maintaining that data for you on that electronic page. And there is some invisible thread which is continuously, without your asking, without your clicking that spelling option, there is an invisible spelling thread which is continuously, without your permission even, continuously checking the spellings of your data. So likewise, there are certain invisible threads which continuously work for you, work for the interface without even clicking or without even asking for your permission. As soon as you start or initiate a software or a program, they start working with the initiation of that software. As soon as you click a software, as soon as you click an option, these invisible threads just get awake and they start their work. Likewise, you can take an example of a notepad. And notepad is, you know that its interface is like an MS Word software, and you can write down something on notepad. So in notepad program, one thread will be taking the user input. Its white interface, its white electronic page would be taking the user data continuously, and another invisible thread will be printing a document or an instruction like that. So point to ponder upon is that a program or software is there. When you initiate or click any instruction, that means you have started a process inside that program. If you click multiple options or multiple instructions inside a software or a program, that means you have started multiple processes. Then because the CPU, after you would click that instruction, CPU would start execution of that instruction. CPU would start applying that instruction on your data, and that would be called as a process. And inside every process there would be multiple threads, one or multiple threads. When you click an instruction starts, or CPU applies that instruction on your process, there are certain invisible instructions which are working at the back end. So you can say that a program is like a company or like an organization, and processes are like buildings. Program or software is like a company which has multiple buildings. These processes are like buildings, and every building has multiple rooms inside it. So these threads are like rooms. A company has multiple buildings, and multiple buildings have multiple rooms inside them. So company is like a program or software, and buildings are like processes, and rooms are like threads. So a person residing inside a building, which is actually sitting inside one room, can use the resources of other resources present inside that building. Means one thread can use the resources being used by the other threads inside a process. So that's why we say that it is much easier for different people in one building to work together, as they have easy access to each other and that building's resources. One person residing in one building can access to the resources of that same building, can meet with the people residing inside that same building. So a program can have multiple processes, and a process can have multiple threads inside it for execution. Again, continuing with the example of a notepad. Suppose you run a notepad program. It is like an MS Word software. Operating system creates a process. When you run a notepad program, or even you run an MS Excel program or MS Word program, you run any software or program, when its interface opens up, we can say that as soon as you click a software, its interface actually opens up. At that time, we say that operating system creates a process and starts the execution of main thread of that process. Main thread means the main thing of any software or program is its interface, the window on which you work, the window of that software on which you click certain options or instructions. So the basic cheese which starts or initiates when you click a software is its interface. So interface actually creates its first process. A process can have multiple threads. Each thread will have its own task and own path of execution in a process. For example, in a notepad program, one thread will be taking user inputs and another thread will be printing a document. All threads of the same process share memory of that process. As told you earlier, that a process is like a building, and threads are like its rooms. So a person standing in one room or residing in one room can use the resources of other resources of that building, or a person sitting in one room can go to some other room too for taking something from that room. That's why we say that threads of same processes can share memory space of other processes too, inside that of other threads to inside a process, and threads of the same process can communicate. Communication takes place between them as fast as possible, and multiple threads can exist within one process, and they can also share resources such as memory space. Again and again we are repeating the points. The diagram here displayed on the screen, you can see that in this diagram operating system is controlling multiple programs, and inside multiple programs operating system is controlling multiple processes. And you can see that there are three processes: process 1, process 2, and process 3. And process 1 has 3 threads working inside it. T1, T2, and T3 means thread 1, thread 2, and thread 3. So a process can have multiple threads working inside it. Again, I'll give you an example of MS Word, that if you are suppose applying an instruction on your data, and that instruction is font size, you want to change the font size of your data. Now, what are the invisible threads which are actually working behind the MS Word interface? When you click that option, some other threads are already working there. When you click the option or instruction of font size, the threads which are working behind the scenes are: number 1, the invisible thread of MS Word interface, the thread which is continuously loading that white electronic page or window in front of your eyes. That is one thread. Another thread is of spelling checker. Another thread is spelling checker or spelling checking thread, which is continuously checking the spellings of your data even without your permission. When you make any mistake, spelling mistake in your data, a red underline comes under your word or sentence. So an invisible spelling checking invisible thread is continuously working behind the scenes. Another invisible thread can be like of space checker. When you give too much space between the words inside a sentence, a green underline appears under those words or sentences, a green underline. So how these invisible threads are working? Actually, you already do some settings inside MS Word or inside MS Word Word option. You actually do some settings. In those settings, you actually perform some settings regarding those instructions. And when you tick some instructions, actually these instructions are continuously being used during the program's duration. When you work on that program, those invisible instructions which actually you already set in your MS Word settings, those invisible instructions continuously work. So in order to make things more clear, we can talk about some differences between process and thread on the basis of certain criteria. And you can see these criteria written under the basics for comparison. We are comparing process and thread on the basis of these criteria. So the first criteria is description. Process can be referred to as a program in execution. A process is a program on under execution. When you click an option inside a program and that instruction or option is then applied by the CPU on your data, that means CPU is executing your data along with that instruction, as CPU is applying that instruction on the data. So the data is executing as well as the instruction is getting executed by the CPU. So a process is a program under execution by the CPU, while thread is a part of a process. It is a subset of a process. It resides inside a process, a component of a process which is the smallest unit of execution. How come it is the smallest unit of execution? That is very obvious. As we say, a process is a program under execution. So process is getting executed by the CPU. So a process has certain threads inside it. So when the CPU is executing a process, that is obvious that inside that process threads are also getting executed. So the second criteria on which we would compare these two things is context switching time. Process requires more time for context switching as they are heavier, while thread requires less time for context switching as they are light, as thread is lightweight than the process is. Now you need to understand that what is context switching. In our third lecture or second lecture, we have already discussed that context switching is that when CPU shifts from one process to another process, when CPU executes one process and the quantum or time slice of that process expires, then the CPU after the expiry of that quantum of the process number 1, CPU shifts to process number 2 for execution. So after executing the process number 2, if the CPU shifts back to the process number 1, the CPU would be able to resume the process number 1 from the place where it actually left that process. So the third comparison between the process and thread would be on the basis of sharing of components. Processes possess their individual program counter and registers. Now you already know that program counter and registers, these all are present or built inside the CPU. You already know that CPU has certain bars like ALU, CU, one type of cache, and other things are temporary memories, are registers. So program counter is also a type of a special purpose register. So a process maintains its own program counter and registers inside the CPU when CPU executes that process, while a thread shares the code section, the address section, and data section with the other threads. When a thread is getting executed, as thread is part of a process, so when a process is getting executed by the CPU, a thread is also getting executed by the process, but a thread shares its code section. Code section means binary section of the data, address space, address of that process, and data section with the other threads. Means threads are sharing their data with other threads too, while the process is not sharing its data with other processes, while a process is individually separately maintaining its own things. Then processes are wholly and fully and completely independent and run in a different memory space than the thread. As we have already discussed that processes do not share their things with other processes. They do not share their things, like they maintain their individual program counter, they maintain their individual registers, they maintain their separate memory space. Processes do not share their memory space among them, while threads share each and every thing among them. One thread shares its code section, data section, address space, as well as its memory space with other threads. Likewise, two processes running on the same system at the same time do not use same address space. Very simple, because as already said, processes do not share anything of their own with the other processes, while threads share each and everything of their own with other threads. So of course threads would run within a process using the same address space. One thread can use the address space of other thread, while every process has its own data segment, has its own separate data segment, while all threads within the process use the same data segment of their process. Means a thread exists or lies inside a process. Thread is part of a process, so a thread can use the data segment of its process. So likewise, an individual process can be independent of other processes, as they do not share their things. Processes do not share their things among them, so they are independent of one another. They are not dependent on one another. They are totally independent of one another, while threads are parts of a process and so are dependent on a process. Thread is subset or part of a process, so thread is actually dependent on the process. It actually uses its address space or uses its data segment. So one thread can read, write, and modify another thread inside a process. While processes require more time for termination and threads require less time for termination, the communication that takes place between the processes needs some time because they are heavier, and the communication takes place between the threads requires lesser time for termination than the process because threads are lightweight. If a process gets blocked, remaining processes can continue execution. As already told, that processes are totally independent of one another. So if one process gets blocked, the remaining processes can continue their execution independently, while threads are dependent on one another. So if one thread gets blocked, all of its other same peer threads inside that process would also get blocked because they are interrelated, they are dependent on one another. If one gets blocked, the other definitely gets blocked. While the processes require more resources, more CPU time or more memory space, etc., while threads require fewer resources because they are lightweight and they reside inside a process. Processes require more time to create, while threads require less time to create as compared to the process. Likewise, other differences are that different processes have different copies of code and data, their binary code and their data. So different processes have different copies, as each process is working on a different section of the data, or each process is like an independent instruction, an independent option. While sharing some copy of code and data can be possible among different threads when it comes to the threads. So they can share same copy of code and data among themselves. Processes do not require synchronization. We are repeating that again and again, as processes are independent of one another, so they do not require synchronization. They are independent of one another. While threads require synchronization to avoid unexpected scenarios. As threads are interrelated, they are dependent on one another, so they require synchronization. Processes can only exercise control over child processes. Here I want to add an important point here, that every process has a sub-process. Every process has a child process. There is a concept of parent process and child process. Parent process and child process. Parent process is actually producing child process or children processes. So any change in the parent process does not affect the child process because every process is independent of one another. While in threads, any change in the main thread may affect the behavior of the other threads of interrelated threads inside a process. So as threads are interrelated, so change in one thread can affect the behavior of other threads too. So process is controlled by the operating system. Process is getting controlled by the operating system, because when you apply an instruction or option on the data, that is directly being controlled by the operating system. Operating system controls the data, operating system controls the instructions or options. While threads are part of the process, so they are controlled by the user of the option, the user who is actually using the program. So the threads are used are controlled by the programmer or user of a program, while the processes are controlled by the operating system itself. So till now, dear students, we are done with the concept of a process, a program related with the concept of threads. We are done with the concept of threads. You must have got this idea that what actually is a thread and what is the difference between a thread and a process, because we have extensively discussed the differences between a thread and a process. If you've got the concept that threads are part of a process, threads are actually subsets of a process, they reside inside a process, then you are ready to move towards the concept of multi-threading. As the name is indicating, that multi-threading is something to do with a thread, And you can guess it very easily that as we've already said that a process has threads inside it. A process can have just one thread inside it, and a process can have multiple threads residing inside it too. So a thread is a lightweight process that is part of a process. A thread resides inside a process. A thread is subpart of a process. And multi-threading is an execution method of a program that allows a single process to run multiple threads at the same time. Means, as said earlier, that a process can have multiple threads inside it. And multi-threading is the ability of a process to run or execute multiple threads at the same time. The main purpose of multi-threading is to provide simultaneous execution of two or more parts of a program to maximum utilize the CPU time. That is easy to understand that if a process has two threads inside it and both the threads are activated, it simply shows that inside a program, two threads means two invisible instructions or two options or two parts of the program are getting executed at the same time. As here you can see in this diagram that there are two processes of a program, process number 1 and process number 2, and each process has two threads working inside it. You can see that process 1 has two threads working inside it or residing inside it, thread A and thread B, while process 2 already has two threads residing inside it, also namely thread A and thread B. So the main purpose of multi-threading is to provide simultaneous execution of two or more parts of a program to maximum utilize the CPU time. Means if a program is running multiple threads at the same time, means multiple instructions are working at the same time, multiple instructions are getting executed on the data of that program at the same time, which means that CPU is working at maximum, as CPU is dealing with one thread, executing another thread, then executing another thread, then executing another. So the CPU is utilizing its time at maximum. Its CPU as a resource is getting utilized by these threads. CPU is not getting any spare or idle time. A program can be divided into two or more parts that can run concurrently, simultaneously at the same time, and each part of such program is known as thread. As processes are parts of thread, indirectly threads are also part of a program, because threads are inside a process and a process is inside a program. So threads are indirectly part of a program. When these threads execute simultaneously or concurrently for accomplishing a task is known as multi-threading. In multi-threading, every thread has a priority between them. Means the thread which is getting the higher priority would be executed first, at first number by the CPU. The thread which is getting any low priority by the CPU would be executed afterwards by the CPU. So thread with highest priority get preference over the low priority thread for execution. Multi-threading is the ability of a program or an operating system process to manage its use by more than one user at a time, and to even manage multiple requests by the same user. Why we are saying that multi-threading is the ability of a program to manage multiple requests by the same user? It means that if a user is applying multiple instructions on the data, that simply means that that same user is requesting multiple things from the computer, from the CPU. Now, You can see that diagram or hierarchy on the screen. Now let us take into consideration the benefits of multi-threading. Multi-threading increases the responsiveness, as if one thread of a process is blocked or performing the lengthy operation, the process still continues, because if one thread is blocked, the other thread would be executed by the CPU. The second benefit of multi-threading is resource sharing. As already told you that threads are interdependent, threads are interrelated with one another. One thread shares its resources with other threads, or all the threads share their resources with one another, and threads can also share memory space or code section or data segments with one another. So the second benefit of multi-threading is resource sharing, as several threads of a process share same code and data within the same address space. To understand the concept of multi-threading clearly, let us take an example of a word processor like MS Word. Our word processor, as you know, that displays graphics, responds to keystrokes or commands, and at the same time it continues spelling and grammar checking behind the scenes invisibly. You do not have to open different word processors to do or perform these things at the same time, simultaneously or concurrently. It does happen in a single word processor with the help of multiple threads. Means inside one MS Word program, you can use dozens of options, you can use dozens of instructions, you can use dozens of threads. So a user is typing a paragraph. I'm giving you a supposition, an assumption that a user is typing a paragraph on MS Word, but in background one more thread is running and checking the spelling mistakes. Another thread is responding to the keystrokes you are pressing. For example, you are writing an essay. So for writing an essay in English, you are continuously pressing the alphabet keys, and your spellings are getting checked by an invisible thread, and your grammar is being checked by an invisible thread. And another invisible thread is continuously checking the graphics, or continuously making the graphics available to you, or making the interface. Here in terms of graphics you can say interface, it means interface. An invisible thread is continuously maintaining that white screen or your background color or background page or graphics for you. So these all threads are working invisibly behind the scenes at the same time. Grammar checking thread is continuously working behind the scenes on your data. You are pressing the keys and you are writing down alphabets, different alphabets in order to write your essay on the MS Word electronic page. So an invisible thread is continuously taking or interpreting your keys data. Another invisible thread is continuously maintaining your white screen or interface, MS Word interface or MS Word window in front of you. So it does happen in a single MS Word software interface with the help of multiple threads. A user is typing a paragraph in background. These all threads are running continuously. As soon as user is doing a typing work, the other thread notifies the user about the spelling mistakes. So the CPU is handling multiple threads at the same time, executing one thread, then the other, and it goes on and on. After multi-threading, now let's talk about the phenomena of multi-programming. You must be aware of this concept because in types of an operating system, we already talked about multi-programming operating systems and multitasking operating systems. So in order to clearly understand these phenomena, you need to actually again go through that lecture. So what is multi-programming? In multi-programming, many programs are loaded in memory. Multiple programs are loaded into the main memory RAM, but the CPU only executes one program at a time. In multi-programming, multiple programs are loaded in the RAM at the same time, but the CPU is only executing one program at a time. If two programs are loaded into the RAM, one program is MS Excel and another program is MS Word, the CPU would properly and completely execute one program, and after completely executing the one program, it would go towards or move towards the other program. So other programs wait until the previous program is executed. Operating system arranges the jobs, tasks or programs inside RAM in a way that the CPU will always have one task or one job to choose and execute. Here, the concept is that operating system stores multiple jobs, tasks or programs in the memory at the same time. To process or execute these tasks or jobs, the CPU selects one of them and starts to execute that job or task in the memory. Ultimately, if one job belonging to a program has to wait for a specific time period for some other task to finish, like input-output operation or other instruction, the CPU switches to the other task or job belonging to the same program for that time period. Regardless, in a non-multiprogramming system, the CPU must be resting in an idle state. But in a multiprogramming operating system based environment, the CPU is not resting at all because the CPU is switching back and forth between multiple tasks and jobs for execution. But remember that is very important, that in multiprogramming phenomena, in multiprogramming operating system based systems, the CPU would be switching back and forth between the tasks or jobs of one similar program, because CPU would be bound to first attend the tasks or instructions or options or jobs of one program completely. Then afterwards the CPU would move towards another program or the tasks or jobs or instructions or subparts or subprograms of another program. It will completely attend the instructions or subparts or subprograms or subtasks of one program. Then it would attend the subparts or subtasks or instructions of another program. Like I gave you an example of MS Word and MS Excel. It would in multiprogramming environment, in multiprogramming phenomena, the CPU would completely execute or attend the instructions of MS Excel, and after completely executing the processes or instructions or subparts or subtasks of MS Excel, it would move towards the MS Word, and it would then execute the tasks or jobs or instructions or sub-instructions or subparts of that MS Word program. The advantage of multiprogramming is that it saves users time in loading the programs to main memory RAM and runs the programs quickly. The only drawback is that the system requires more main memory as it is occupied by many programs. Of course, as said earlier, that multiprogramming supports the loading of multiple programs at the same time inside RAM. In multiprogramming, multiple programs get loaded into the RAM. So of course, if they have got huge capacity, they will of course they will occupy the space of RAM. So the shortage of space can occur in RAM at that time. Sometimes bigger programs or softwares of huge capacities cannot fully load into the main memory RAM, and thus programs can run slowly. So multiprogramming can make your RAM slower. For example, when a user loads program 1, say MS Word, and program 2, say MS Excel, the CPU is able to execute only one program between MS Word or MS Excel. In a multi-programmed system, as soon as one job goes for an input-output task, the operating system interrupts that job, chooses another job from the waiting queue, from the job pool, and gives CPU this new job and starts its execution. The previous job keeps doing its input-output operation while this new job does CPU-bound tasks. Now, say the second job also goes for an input-output task. The CPU chooses a third job and starts executing it. As soon as a job completes its input-output operation and comes back for CPU tasks, the CPU is allocated to it. In this way, no CPU time is wasted by the system waiting for the input-output task to be completed. Means if one task of a program, another task of a program, and third task of that same program want to get executed at the same time by the CPU, but one task is then engaged with input-output operation, another task is available to the user, to the CPU would start its execution. When that second task would also go for input-output operation, CPU would fetch the third task or job for execution. When that third task or job gets busy with input-output operation, the CPU again fetches the first job or task for execution. So the CPU never sits idle. The CPU never lays back or never gets a rest. It executes either one job or task or another job or task or third and so on. But in multiprogramming, the CPU executes the tasks or jobs of one program, and after executing the tasks of one job or one program or software, then it moves towards the tasks or jobs of the second program. So therefore, the ultimate goal of multiprogramming is to keep the CPU busy as long as there are processes ready to execute. This way, multiple programs can be executed on a single processor or CPU by executing a part of a program at one time, a part of a program after this, then a part of another program, and so on, hence executing multiple programs. Hence, the CPU never remains idle. As you can see in this diagram, as we were saying that the ultimate goal of multiprogramming is to keep the CPU busy. If in a multiprogramming operating system there exists only a single CPU or a single microprocessor, then that single microprocessor at one time would execute one part of a program, then another part of a program, then another part of the same program. But suppose there is one single CPU and there are three programs. Suppose MS Excel, MS Word, and MS Paint, three programs. Program A is MS Excel, program B is MS Word, and program C is MS Paint. Three programs are actually loaded inside the main memory RAM. So the CPU would actually execute these programs one by one. As you can see in this diagram, that the microprocessor would attend or would fetch or grab a program for execution as per the priority queue or as per the waiting list. Suppose in that RAM, the first place in that waiting queue has been occupied by process A. The second place in that waiting queue is occupied by some other process. And third place, you can correct these diagrams. There is, suppose, process A, there is process B, and there is process C. So according to the priority list or waiting queue inside the RAM, the microprocessor will execute the tasks of these programs. Now, dear students, we are done with the multi-threading. We are done with multi-programming. Multiple threads reside inside a process. Multiple programs reside inside a RAM, and CPU execute them one by one at a time. Now the concept arises is of multitasking. Multitasking is viewed as the logical extension of multiprogramming. How it is the logical extension of multiprogramming? Because multiple programs have multiple jobs or multiple tasks inside them. Suppose there's a program, MS Word. Now, MS Word has certain other tasks or instructions inside it. If we click those multiple tasks, those multiple instructions, that means we are creating multiple tasks or multiple processes for that program or software. So a program can be divided into multiple parts or multiple tasks. So that's why we say that multitasking is the logical extension of multiple programming, as it implements the same approach of switching between the jobs, but here switching is very often. Multitasking is a function of an operating system that loads multiple programs, that loads multiple processes, multiple tasks, or multiple threads in main memory RAM and executes them at the same time by rapidly switching the CPU among them. This means that a program has multiple tasks. A program is divided into multiple tasks or multiple subtasks or subparts or subjobs. Now this what the CPU would do. CPU would attend this subtask 1 of that program, then subtask 2 of that same program, then subtask 3 of that same program, then subtask 4 of that same program. So the CPU would execute all those subparts or multiple tasks or jobs of that same program, but one by one, and CPU would rapidly switch between those multiple tasks at such great speed in nanoseconds that the user would not be able to catch that speed. User would not be able to understand that the CPU is actually switching between those multiple tasks. It would look like to a user that a CPU is executing those tasks at the same time. It would appear to the user, but actually that would not be the phenomena. CPU is not executing, would not be executing those multiple tasks at the same time, but it would be executing those tasks at such great speed that the user would think that the CPU is executing those tasks at the same time. So the multitasking operating system assigns very obvious that it assigns quantums or time slices to those tasks or jobs. The operating system is able to keep track of where the users are in these tasks. Talking about the context switching, that where the CPU would left the execution of one task, it would resume or again start the execution of that same task from that same point. So the operating system is able to keep track of where the users are in these tasks and go from one to another task without losing information through context switching among them. Each running task takes only a fair quantum of CPU time. It permits multiple users to share common resources simultaneously. And it means CPU time is a resource. CPU is a resource. All the subtasks or multiple tasks of a same program would want to use the CPU for execution. So the CPU would share its resource. CPU would share its time, its quantum, its slices among all those multiple tasks. And CPU executes each task as per allotted or assigned time slice or quantum. So CPU permits multiple users to share common resources simultaneously. Here also basically a context switching is occurring, but it is occurring so fast that the user is able to interact with each program separately while it is running. This way the user is given the illusion that multiple processes or tasks are executing simultaneously. As I've told you earlier, that CPU would be executing each and every task separately, independently. CPU would not be executing all those multiple tasks at the same time, but CPU would be executing all those tasks at such great speed that it would happen or occur to user would think that the CPU is executing all those tasks at the same time, and that is of course not true. So this way the user is given the illusion that multiple tasks are executing simultaneously, but actually only one process or task is executing at a particular instant of time. Since the switching in these systems is very fast, the users are not able to notice it, and it gives the perception of a dedicated system. In the modern operating systems, we are able to play MP3 music, we can edit documents in MS Word, we can listen to the music, we can Google search something through our Google Chrome browser. So we can perform all these multiple tasks at our laptops, on our smartphones at the same time by using the multitasking operating system. So our smart devices nowadays are actually able to perform multitasking. They can handle our multiple tasks. So this is accomplished by means of multiple tasking. You can see this diagram on the screen. In a time-sharing system, multitasking actually happens. Time-sharing operating systems actually perform multitasking. So in a time-sharing system, each process is assigned some specific quantum of time for which a process is meant to execute by the CPU. Say there are 4 processes, P1, P2, P3 and P4. These 4 processes, P1 to P4, are ready to execute inside the RAM. So each of them are assigned some time quantum or time slices by the CPU for which these processes will execute. For example, time quantum of one process is 5 nanoseconds. Likewise, some time or quantums are actually allotted to all the processes. As one process begins execution, say process 2 begins the execution, it executes for that quantum of time, 5 nanoseconds. After 5 nanoseconds, the CPU starts the execution of the other process, let's say process 3, for the specified quantum of time. Thus, the CPU makes the processes to share time slices between them and execute accordingly. As soon as time quantum of one process expires, another process begins its execution. Like the time quantum of process number 2 was 5 nanoseconds, and the CPU executed the process 2 for 5 nanoseconds, but when the 5 nanoseconds expired, the CPU automatically shifted to the process number 3 or to the next process for execution. In a more general sense, multitasking refers to have multiple programs, multiple processes, multiple tasks, multiple threads running at the same time. This time is used in modern operating systems when multiple tasks share a common processing resource. So these multiple tasks can share the CPU time like quantums. They can use these multiple tasks can share the memory, like all the multiple tasks are loaded into the RAM memory. So that's why we can say that all the multiple tasks are sharing the RAM space. As depicted specifically in this image, at any time the CPU is executing only one task. This picture actually properly relates to the centralized network or server-based network in which there are 3 terminals, there are 3 workstations, or there are 3 client computers connected with a server computer CPU, terminal A, terminal B and terminal 3. These 3 are basically 3 different client computers inside a server-based network. Now the server's CPU is actually executing the task of terminal A, then the task of terminal B, then the task of computer number 3. Then again that CPU is, after the quantums expire of the processes or tasks of terminal A, B and C, the CPU again executes the program or the process or the task of terminal number A or terminal number B and terminal number 3. Then again terminal number A, the program or process of terminal B, and then again the program or task or job of terminal A, B and C are again executed by the CPU, one after the another as per the allotted time quantum. At any time the CPU is executing only one task, then the other, like a CPU is executing the task A, then task B, then task C, while other tasks are waiting for their turn. The illusion of parallelism is achieved when the CPU is reassigned to another task. That is, all the 3 tasks A, B and C are appearing 2 to get executed, appearing to execute or appearing to execute or occur simultaneously by the CPU because of the time sharing. In order to give you more clarity, let's discuss the differences between multitasking and multi-threading. The first difference between multitasking and multi-threading is that multitasking lets CPU to execute multiple tasks at the same time. Not at the same time exactly, but it occurs to user that the tasks are being executed by the CPU at the same time. While in multi-threading, multiple threads are being executed by the CPU. These threads are belonging to a process, so these multiple threads can be executed by the CPU at the same time. In multitasking, CPU switches between the programs frequently. We are talking about the context switching. So multitasking is supporting the phenomena of context switching, while in multi-threading, CPU switches between the threads frequently too. But in multitasking, the CPU switches between the programs. In multi-threading, the CPU switches between the threads. In multitasking, system has to allocate separate memory and resources to each program or each process that the CPU is executing, while in multi-threading, the threads can share the memory space or memory address between them. We can say that system has to allocate memory to a process. Multiple threads of that process share that same memory space of that process among them. Multiprogramming. Now we have discussed the differences between multitasking and multi-threading. Now we are going to discuss the differences between multiprogramming and multitasking. Multiprogramming enables multiple programs to utilize CPU simultaneously. Multi-programs can get loaded into the RAM at the same time, utilizing the CPU at the same time, utilizing the RAM space at the same time. While in multitasking, a supplementary form of the multiprogramming is multitasking. In multitasking system supports actually user interaction. It supports the CPU executing multiple programs at the same time. In multiprogramming, multiple programs can get loaded into the RAM at the same time, while in multitasking, multiple tasks can be executed by the CPU at the same time. It's an illusion, but we can say at the same time. In multiprogramming, improvement in CPU utilization. As multiple programs are being handled by the CPU, it handles one program completely, then afterwards CPU handles the other program. In multitasking, it minimizes the response time, but it does not improve the CPU utilization. Multiprogramming occurs when the currently running process stops. It supports multiprogramming supports this phenomena of switching, that when the currently running process stops, then the other process starts. When CPU stops the execution of one process, then it switches to the other process or program or task for execution. While in multitasking, multitasking is carried out each time after the time slice of a process is finished. In multitasking, the CPU takes care of the quantum. When the time slice or quantum of one program or task expires, then CPU switches to another task or job for execution. While in multiprogramming, it takes care of the number of tasks of a program. When one task gets completed, then one program gets completed by the CPU, then it shifts to the other program. Multiprogramming is simple, multitasking is complex. We have discussed multi-threading, we have discussed multi-programming, we have discussed multitasking. Now we are going to discuss multiprocessing. That is very, very simple. Multiprocessing is really very simple because, as the name is indicating, multiprocessing means multiple processors, multiple CPUs. In a uniprocessor system, a computer which has only one CPU installed inside it, so in a uniprocessor system, only one process executes at a time. Multiprocessing is the use of two or more CPUs. It is the use of multiple CPUs within a single computer system. Multiprocessing means adding more number of CPUs or processors to the system, and adding more number of processors or microprocessors or CPUs inside the computer increases the computing speed of the system, as multiple CPUs would be able to handle multiple tasks at the same time. An operating system has the ability to multi-program, where it can involve multiple programs to be executing over a single CPU. A multiprocessing system is one which has more than two processors. The term also refers to the ability of a system to support more than one processor within a single system. Now, since there are multiple processors available, multiple CPUs available, multiple processes, multiple threads, multiple tasks, multiple jobs, multiple programs can be executed by these multiple CPUs at the same time. One job or one task would be handled by one CPU. Another job or task would be executed by another CPU. A third task or job would be executed by a third CPU. So these multiprocessors share the computer buses, CPUs clocks, memory spaces, and input-output devices, etc. So, with the help of multiprocessing, many processes can be executed simultaneously. Say processes like, assume process like P1, P2, P3 and P4. These are 4 processes. So process 1 till process 4, these 4 processes are waiting for execution. Now in a single processor system, what would happen, that a single CPU would execute these all 4 processes one by one. Like the CPU would execute I'm talking about a system which has only a single CPU. So if a system has single CPU, it would first execute process 1, afterwards process 2, then afterwards process 3, and after process 3 it would execute process 4. But in a multiprocessor system where exist multiple processors, what would happen, that each process would be assigned to a different CPU for its execution. Process 1 would be assigned to CPU 1, process 2 would be assigned to CPU 2, process 3 would be assigned for execution to CPU 3, and process 4 would be assigned for execution to the process number 4. So with multiprocessing, each process can be assigned to a different to a microprocessor or to a different CPU for its execution. If it's let's suppose a computer is a dual core computer which has 2 processors. So both of the processors would handle two processors each. One CPU would handle 2 processes, the other CPU would handle the other 2 processes. So the 2 processes can be executed simultaneously and thus will be 2 times faster. Similarly, if there is a quad core computer system which has 4 CPUs inside it, each CPU would be able to handle 1 single process each, and that quad core processor computer would be 4 times faster than the single processor computer. So this diagram is very easy to explain. This diagram is also there in order to give you the clarity about the working of multiple systems, in order to give you the clarity about the working of multiple processors. Like there are multiple processors present there. There are 3 processors or CPUs present there: CPU 1, CPU 2 and CPU 3. Now you can see that there are 3 processors or CPUs present inside a computer, and there is only one program which the user is using, that is Google Chrome. And that Google Chrome is again and again being used by the user, and the user is applying different instructions on that program. So the program is further divided into 6 subtasks, 6 subparts, 6 subprograms, or 6 processes. Now what can happen? There are 6 processes, 1 program, and 1 program has further 6 subtasks, subprograms, or sub-processes. This one program is divided into 6 parts, and there are 3 CPUs available. So 3 CPUs can handle 6 processes, means each CPU would be able to handle 2 processes each. CPU 1 would handle 2 processes, CPU 2 would handle other 2 processes, and CPU 3 would handle other 3 processes. Each CPU would assign some quantum or time slice to a process, and as per that allotted time slice or quantum, that CPU would execute each and every process. But suppose there happen to be we happen to have only one single CPU. There is only one single CPU and there are 6 processes, so that CPU would consume more time, would take more time to execute these 6 processes. While if a computer has more than 1 processors of CPUs, like 3 or 4 or 7 processors, that system would be able to execute these parts more easily in short amount of time. Now let's talk about the difference between multiprocessing and multithreading. So multiprocessing has multiple CPUs present inside it to increase the computing power. So multiprocessing means multiple processors or CPUs are there. While in multithreading, it creates multiple threads inside a single process. In multithreading, there are present multiple threads inside a process. In multiple processing, there are present multiple CPUs or processors inside a computer system. In multiprocessing, multiple processes are executed simultaneously at the same time by multiple CPUs. If there are 3 processes present and there are 3 CPUs inside a computer, these 3 CPUs can execute those 3 processes at the same time. All those 3 CPUs would be executing those processes at the same time parallelly. This is called as parallelism. So in multithreading, multiple threads of a single process are executed concurrently. In multiprocessing, multiple processes are executed by multiple CPUs, while in multiple threading, multiple threads of a single process are executed at the same time by the CPU. In multiprocessing, creation of a process is time consumed and resource intensive. Process creation is always heavier and it takes more time or weight. While in multithreading, creation of a thread is economical in both time and resource, because thread creation is really very easy because threads are lighter, while process creation is a bit heavy than the threads creation. So in multiprocessing can be symmetric or asymmetric. Multithreading is not classified. Final points. These points would totally clear your concepts in terms of differences. Multiprogramming, we would classify these differences between multiprogramming, multitasking, and multiprocessing. Like in multiprogramming, you can say that multiprogramming executes same programs by one processor or CPU. Multiprogramming executes or allows the execution of same program or the subparts or subprograms of the same program by one CPU only. In multitasking allows the execution of multiple processes, multiple jobs, multiple tasks, or multiple programs at the same time by a single CPU. In multiprogramming, the CPU is one, but it is bound to execute one program. It is bound to execute all the tasks of one program, then the tasks of another program. While in multitasking, the programs have other different subparts or subprograms or subjobs, and these CPUs can be, or one single CPU can just switch between them. In multitasking, the CPU does not take care about the program, that it is not bound to just execute the tasks of one program. No, it's not like that. It executes some task of one program, and then it also executes some tasks of another program. While in multiprocessing, it allows the operating system what allows a computer to execute or CPU to execute multiple programs, tasks or jobs at the same time with the use of multiple processors or CPUs. Multiprogramming, one CPU can handle one program at a time, or one CPU can handle subparts or subtasks of only one program at a time, then the subparts of or subtasks of another program afterwards. While in multitasking, single CPU can handle multiple programs at the same time. I've told you earlier, this is very important difference, that in multiprogramming, the CPU is bound to execute all the subtasks of one program, then afterwards the subtasks of another program. While in multitasking, that is not the case. CPU can handle the subtasks of multiple programs at the same time. The CPU can handle the subtasks of one program and the subtasks of another program, then the subtasks of another program intermittently. Means in multitasking, the CPU can handle multiple tasks of multiple programs at the same time, while in multiprogramming, the CPU can handle the multiple tasks of one program only at a time. In multiprocessing, multiple CPUs or processors handle multiple programs at the same time. Multiple CPUs are busy with multiple programs. In multitasking, one CPU is busy with multiple programs, while in multiprogramming, one CPU is busy with only one program. As you can see in the last row, this is the end point, that in multiprogramming, one single CPU or one single processor is busy with one program only at a time. One single CPU or one single processor is busy with the subtasks of one program only at a time. When it would be done with the subparts or subtasks of that one program, then it will move towards the another program. While in multitasking, that is not the case. One CPU or one processor is busy with multiple programs at the same time. One CPU or processor is busy with multiple tasks of multiple programs at the same time. While in multiprocessing, multiple CPUs or multiple microprocessors are busy executing multiple tasks of multiple programs at the same time. Hope now the difference is clear to you. So, dear students, now we are done with our chapter number 1 successfully. Hope you have got all the concepts, you have absorbed all the concepts. Today we have finished this chapter completely. The exercise of this chapter would be discussed with you people in an online class, in an online live session, and inshallah after Eid we'll be starting with our next chapter number 2. But before that, you need to submit your assignments. We will inshallah conduct an online test too, and the exercise would also be discussed in an online session, inshallah. So, signing off for now. May you have a happy and blessed Eid. Stay safe, stay healthy on this Eid. Stay foodie. Allah Hafiz.